Okay, so today this is the 8th week of this live interactive sessions for this particular course of fluid dynamics for astrophysics, and I am Sripan. I am working as a PMRF at ITBHU and conducting this live sessions once in a week is one of my deliverables towards my fellowship. Okay, so so today. As usual, we are going to solve some objective type questions, and while solving the questions we will try to discuss a few things which will enrich our knowledge. Okay, so let us move to the first question. So let us have two active galactic nuclei. So first of all, what is an active galactic nuclei is, let's say we have the galaxy called Milky Way, right? So whether it is active or not, how do we determine that is whether it is accreting the material around it towards its center. So if it is in its active state, then we expect to that the galaxy must converge to a point, and therefore it will collapse, right? So that is for active galactic nuclei. Now the Milky Way does not have that kind of property, so this is it is not in the active state right now, so therefore it is stable, right? Now another question is, so in active galactic nuclei what happens is, you have to start with, you have a center where you have a supermassive black hole which will have some mass of 10 to the power 6 of the solar mass, and then if this is black hole, then what happens is there is an accretion disk around it, right? So how this accretion disk is formed is, so whatever it is accreting, it will have some inherent angular momentum with it, right? So if it is trying to fall towards the black hole, what will happen in for having the total radial motion, it should lose its angular momentum first, right? So but by virtue of angular momentum, it will try to rotate again and again in a different annulus of the disk in disk like structure, and that will form your accretion disk. Now one have an accretion disk having radius 5 unit, and the radius of the other accretion disk is 5 times larger than that. So first one is accreting material at a speed of 25 units, let's say some unit of these things, and the second one is doing so at a speed of 15 unit. So what is the ratio of accretion rate in these two cases, right? So consider that there is no vertical structuring in density and accretion velocity. So first of all, let us recall the formula of accretion rate in that case where there is no vertical structuring in density and accretion velocity. Okay, so now let us recall this one, that m dot is equals to minus 2 pi, right? Then there will be r, which will be the radius of the disk, and then there is a rho, there is pr, which is the accretion velocity, and then you have a 2h, right? So what is 2h is, so this is disk, right? This is not a plate, so it will have certain amount of height associated with it, which is the height is 2h. Okay, now if this is the case, so now you need to find out the ratio of this in two different cases. Let's say we are giving it m1 dot by m2 dot, right? And then so that means you have r1 by r2, right? And then vr1 VR2. Okay, so this is the case. Now let us recall the values given in the question. So let's say you have a radius 5 unit, okay, and the radius of the other disk is 5 times larger than that. So what does that mean is you have a 5 here and you have 25 because that is the 5 times of R1, and VR1 is 25, right, and the second one is 50. So you need to find out this ratio. Now 25 can cancel out, so you left with 1/3. Okay, so your M1 is 2 into, right, the ratio has to be 1/3. This will be the answer. Okay, now okay, so if this is the case, you can easily just have a moment to have insert. So you have this one here, right? Okay, so just a second, I think I should stay. Okay, next question is here is consider two thin accretion disk A and B. Again, this is a problem with accretion disk, and the mass of the compact object at the core of accretion disk A is core of accretion disk A is 5 times that of B. The pressure at a distance of 10 unit in accretion disk A from the core is 50 unit. Let the height in both cases are same. Now the density of the material accreted in case of B is calculate the pressure at a distance of 5 units in accretion disk. So for doing this problem, first of all you have to recall the formula pressure, right? Now the pressure is given by Gm, right, and then there is a rho, there is that height, rho A square by R cube, right? Now let's say we have a P1, we have P2. So what is called is mass of compact object at the core of accretion disk is 5 times, right? Let's say this is A and this is B. Okay, so you have MA divided by MB, right, into, just a second, okay, my coding is it's fine. Okay, so your PA is this MA by MB, then you have rho A by rho B, right, into RB by RA, and it's Q, right? So this is your, now is 5 times that of, so what does it mean is this is 5 MB by MB into PA, sorry, this is rho A. Now density of material accreted in case of B is 10 times that of A, right? So this is rho A by 10 rho A, right, into RB by RA. So here no. So the pressure at a distance of 10 unit, right? So here I think yeah, so you have RB by RA. So RA is given us, and this is given us 5, this is given us 10, and then PA PB. So you need to find out the PB. So first of all, the PA is here is 50, and you need to find out the PB here, right? Okay, now if this is the case, so you have 50 by PB, so you have 5 by 10, and then you have again 5 by 10, right? So this is half to the power 4, which is 1 by 16, right? So PB will be what? 50 into 16, right? It will be 800, right? That is 16 times the pressure at A. Okay. Now what I can do is just take this here. Okay, now let's move on to the next question here. So in a thin accretion disk, azimuthal and radial flow, there are 4 options. So I was supposed to ask any of the students, but unfortunately today no one is attending the class. So in a thin accretion disk, azimuthal and radial flow both are subsonic. A radial flow both are supersonic, and is supersonic but radial flow is subsonic. And then azimuthal flow is subsonic but radial flow is supersonic. So first of all, we need to understand what is a thin disk. So you have a accretion disk like this. So it has some radius and it has some amount of height also, right? This is h. Now if this h is very small than your radius, that means it is a thin accretion disk, because it does not have such high measurement in this y direction. Let's say you have x and y, you have x here, you have y here, then it does not have much dimension in y. That's why this is an accretion, thin accretion disk. Now you have azimuthal and radial flow, both are subsonic, and then whether this is both are supersonic. Azimuthal flow is supersonic but radial flow is subsonic, and then azimuthal flow is subsonic but radial flow is supersonic, right? So this much things are there. Now my question is that okay, so there is a relation between this h is the height of the disk, h by r, that is equals to cs, which is the sound speed, right, in the localized region, and then you have v5, right? v5 means, so you have accreting materials, so they are moving in some annulus in the disk, right? So that will give you the v5, and also there is some little bit amount of with respect to this v5 there is certain amount of vr also, right, which is the radial velocity. But here this is cs by v5. So now you know the Mach number, let's say m5, which is azimuthal Mach number, that will be defined by v5 by cs, right? So for thin accretion disk, what we have is h by r, that will be less than 1. So that means 1 by m phi, that will be less than 1. So therefore that means m phi is greater than 1, which is for supersonic, right? Because if the perturbation of the flow will have a velocity which is higher than the local sound speed, it is called supersonic flow, right? So azimuthal will be supersonic, but in this case the PR is not greater than CS, rather PR is less than CS. So that means you have the MR which is the less than R, that means this is subsonic, right? Subsonic. Okay, so you have supersonic azimuthal flow and you have subsonic radial flow. Okay, so now let us look at the answers. So azimuthal flow is supersonic but radial flow is subsonic. That is the answer. This is hard, right? Okay, now okay, just have new slide, insert. Okay, so the next one is this one. So can you give me? Okay, so consider the gas from a large star being accreted by its compact companion through a quasi-Keplerian accretion disk. Now the accretion gas has some initial angular momentum, right? So accretion can proceed even if the gas parcel in the disk have zero radial velocity. That is not the case. There should be some radial velocity, but it will not be that much high with respect to the velocity in the azimuthal direction, the velocity with which it is rotating the disk. Okay, so but it will have some finite radial velocity obviously. So first one is not correct. Now the gas parcel in this quasi-Keplerian accretion disk with a finite accretion rate will have a small inwardly directed radial velocity. So the second one is a correct answer for this question. Okay. Now the specific angular momentum, that means angular momentum per unit mass, so of a gas parcel in a quasi-Keplerian accretion disk at radius r1 is greater than that at a radius r2. Now what we need to understand is you need to understand one thing, that is the angular momentum per unit mass. So that is defined as L and then R and P phi. R is the radius of that particular thing and P phi is the azimuthal velocity with which the materials are rotating in a disk having the radius R. Okay, now you have V phi. So what is V phi is R root over Gm by R, right? So inversely proportional to square root of R, right? So L will be higher at higher radius. So that means if you are having in a higher radius, it is rotating in a high radius disk, then that means it will have larger momentum, which is physically intuitive, because as it is coming towards the compact object, it should lose its angular momentum, so it should have larger angular momentum at a larger distance from the compact object, and as it moves towards it, then the angular momentum must be decreasing with the decrement in the radius. Okay, so that's how the scale is proportional to root r. This is exactly the same which our physical intuition is telling us, right? So now you have r1 greater than r2. So for r1 you should have greater angular specific angular momentum, which is of a gas parcel, and a quasi-curved disk is greater than that of r2 if r1 is greater than r2, right? So this should be your correct answer. Okay, now okay, so here you can write answer should be 2 and then 3. Okay, okay, now let's move on to the next one. So you have consider a steady state quasi-Keplerian accretion disk around a compact object. So choose the correct options. So the angular momentum per unit mass of a gas parcel about any an origin or the center of the compact object is proportional to root over r, which is correct. So this is correct one. The scaling is goes as square root. Now angular momentum per unit mass of a gas parcel about any origin, right, at the center of the compact object is no. This scaling is not correct. Then the turbulent eddies in the Shakura Sunayev prescription will be subsonic. So it is true, because in the Shakura Sunayev prescription, the viscosity prescription, the speed of the eddies cannot exceed the sound speed, right? Because in the Shakura Sunayev, what you write is the viscosity stress tensor, viscosity stress tensor, what it will do is, this is T and then R, right? TR phi, that equals to alpha and then P, right? So you have alpha, you have P. Now this alpha here is 0, within 0 to 1. Okay, so within 0 and 1. So alpha is less than 1, so that means the turbulent eddies will be subsonic always. But according to Shakura Sunayev prescription, the viscous turbulent eddies can be supersonic. That is not the case. That is not the correct option to choose. So again, the answer can be written as answer is here is 1 and then it can be 3. Okay, so this is your answer. So this is fine. Now new slide, insert, Okay, so then the next question here is that consider a thin quasi-Keplerian accretion disk with constant uh, m dot, that means the accretion rate is here the constant, and the dissipation rate per unit cross section at a certain radius r1 is d1 and at another radius r2 is d2. Now first of all, let us remind ourselves what is the dissipation rate per unit cross section's formula. So how d is related to our known quantities. So d at a certain radius r is goes by 3 by 8 pi, right? This is 8 pi, and then g m and then this r cube. Okay, 3 by 8 by g m dot r by r cube. So this is your dissipation rate per unit cross section at a certain radius r1 is this. So now if it is the case, so basically what you have is dr proportional to 1 by r, right? So if it is the case, so you have d1, right, by d2 equals to r2 by r1 cube, right? So it is the case. Now r2 by r1 is r2, see there are so many options. So what it is telling that r1 by r2 should be 2. Now here this is then 1 by 2 cube, right? That is 1 by 8. So if it is the case, so you have d2 equals to 8 d1, right? So yeah, so the C is correct here, right? And the disk height h is proportional to r to the power 3 by 2. So we need to recall ourselves those things. So basically what we have is in the formula like P equals to gm by gm rho h square, right? And this is not w, this is h, and there is a r cube, right? And then what you are taking is this pressure is proportional to rho cs square, right? And then if you look at this h square, we will have pressure is rho c square, so you have cs square by gm, and then you have h then you have cs square gm, then you have r cube, right? So if you go by this, we will find out that this is like c is square by gm to the power 3 by 2. So therefore this is h proportional to r by to the power 3 by 2, right? So disk height h is proportional to r to the power 3 by 2. This is also correct answer. So this answer is here C and D. Okay. So new slide. Answer the next question is here. So pick the correct statements. So viscous dissipation primarily hits protons, which then exchange energies with electrons. Directly hits electrons. In Sakura's prescription, the viscous stress can exceed the gas pressure, cannot exceed the gas pressure. So if you remember, just we are discussing that viscous stress T R phi something, so that is equals to alpha P, where P is the gas pressure, and we told that alpha is within this, right? So if it is this, that means TR phi, which is the viscous stress, that cannot exceed the gas pressure. That is one of the answer here. So 4 is correct. And now, so if it is correct, then 3 cannot be correct. Now the question is whether it is hitting the protons or electrons directly. So it will depend upon some length scales, right? So you have viscous dissipations length scale, you have protons and proton collision length scale, electron collision length scale, and electron proton collision length scales. So depending upon those, you will have those interactions, right? Now since proton is heavier than the electrons, right, and you have viscous dissipation. So viscous dissipation being momentum based process, right? So if you can write its answer here. So let's say you have a text box. That you can write the answer here. That answer is viscous dissipation being momentum based process, right, gives more energy to heavier species, right, which is in this case in between proton and electron. It is protons, right, and so okay. Now then what happens is which then exchange, so which then exchanges energy with electrons. Okay, so this is your answer. Fine. Okay, now we can move on to this part here. I think it is your last question. So in a collision of particles with scattering centers, there are 100 particles having energy E0 each. After collision, calculate the probability of 50 particles in the acceleration region having energy 5e. So this is a problem related to diffuse shock acceleration. Okay, so particles collide with scattering centers. So what happens is after each collision, each particle will gain energy, and the ratio of the energy will be beta. So this is E equals to beta E0, where E0 is the initial energy of those 100 particles, and also there is a probability of P, that means you have N0 to start with the particles. Now how many particles will be in accelerated regions, that is depending upon this probability P, right? So now if you calculate this N by N0, that means you have P, right? So you will get an equation like E by E0, right? And you will have a minus alpha here, where alpha is nothing but ln beta, right, by ln p. Okay, so you have n is here 50, fine, and you have n naught that is around 100, and then E is around what? E is 5E0. Okay, so 50 by 100 equals to now 5 E naught by E naught, right, and minus alpha. So this is half equals to 5 to the 4 minus alpha. Okay, so now you can calculate probability from here. How? So you have 5 to the 4 minus alpha, and you have 1 by 2. So how could you calculate it? I think ln 5, something like that, right? So what you basically do is you have to calculate this alpha here. Okay, and to calculate this one, calculate, right? And so basically you have ln beta, something like that. So alpha is this, so ln beta minus ln p, right? So we have half is equals to 5 minus ln beta, right, and then you have plus ln p, so that means ln p, right? So you have half ln beta means 5 minus ln beta is 5. Now beta is basically E by E naught, which is in our case which is 5. So 5 minus, so ln 1 by 5, right? Yeah, and then dot 5 ln p. So you have to calculate this p here. Okay, so calculate p, which is the probability. So with this question, I think I have covered almost everything discussed in the lectures, and also the way these interaction sessions are going on is very disappointing. No one is attending it because of obviously the schedules. Everyone is going to attend the live sessions if the live sessions are before their assignment submissions, but somehow this assignment time is little late for them because they have already submitted the assignments by their own, so no one is reluctant to attend the sessions. However, the sessions will be and the lectures will be available through YouTube, so at any point if someone want to have some look in these questions, because he can look in the YouTube, it will be beneficial for them. So okay, with all this I think we can end today's class, because this much content is there which I can brought with the material, or depending on the material which has been studied in the class for this particular week. So okay, so I think I can stop now. See you on next Saturday. So thank you.